over to Sam. All right, thanks so much. I'll be talking about scalable oversight, continuing from this morning. So the sort of version of alignment or oversight that I'm mostly focusing on here can be pretty well thought of as just fine-tuning foundation models. And so this includes things like classic boring NLP task of fine-tuning BERT for sentiment classification. When you're doing this, you are doing alignment in this definition. You're doing model oversight. But this is a sort of easy case of alignment. It's one where familiar ML techniques work. And I think a key reason for this is that the model is less capable at skills relevant to the task than the people overseeing it. So on my little sort of alignment capability diagram, the model overseers are sort of above the model. They're able to kind of pretty confidently assess that when they disagree with the model's the one that's wrong. And the job of this fine-tuning process is just to sort of drag the model mostly over to the right, mostly just show it what the task is rather than teaching it any deeply new skills. Scalable oversight, again, somewhat redundant with this morning, is the task of sort of doing the same thing of like trying to drag the model over to the right, make it do the thing that you want. In the regime where you assume that it knows more than you do or has sort of is stronger at some skills that are relevant to the task. And this comes up in settings like you want to train some highly capable future generative model to develop new categories of cancer drug or sort of propose new research directions in a pre-paradigmatic field or something like this. And we should expect familiar techniques not to be reliable here because when you disagree with the model, you don't know who's wrong. When you think you agree with the model, you're not actually sure that's because the model is right. Doing this in general is tricky. We're going to want more ambitious methods for oversight, as Jan talked about, probably methods that involve finding ways to use the model's knowledge to then supervise the model. This is obviously sort of an appealing direction, but also one that has a bunch of subtle ways it might break. So I think there's a lot of room for research and figuring out a good protocol here. Developing these methods is going to be hard, messy experimental work. It's work we'd like to get a head start on now, even though these problems aren't really quite arising yet. So how do we get a good head start despite not really yet having these systems? So all the work I'm doing, the evaluation side of the work is following a protocol called sandwiching that Ajaya, who spoke yesterday, proposed a couple of years ago, and we've just been trying to sort of flesh out and try out. The idea of sandwiching is that you first pick a task that's unfamiliar and difficult for typical capable adults, but doable by some expert. So an example I like here is something like read a long, detailed clinical note in sort of medical shorthand and decide what is this person being treated for. This is something where I think if you gave it to me, even with Google, even with an hour, I would be stuck. You then have a non-expert try to use a scalable oversight technique with some current large language model that you think actually has an advantage over the human, has some domain knowledge or skills that we don't have, to train the model on the task. So you're trying to fine-tune the model to sort of get it to do what you want. The trouble is you only have non-experts involved. You're not consulting any doctors. You're not consulting any domain experts at this point. You're not consulting any specialized literature either. You're just trying to work with the model and see how far you can get. The trouble here is that you don't actually know if you succeeded. At some point, the human sort of declares victory, says they finished, they've trained the model, it looks like it works. Then you bring in the expert, they look at what the model's doing and they say, hey, is the model actually giving good medical advice? Is it actually sort of handling this task correctly? And your criterion for success is that the sort of whenever the non-expert human says they're done, they're actually done. They've actually solved the task. So that's the sandwiching paradigm. You're sandwiching the capabilities of the model between two human participants. This thing I've been playing around with a bunch at Anthropic. This is a bit of a detour, but we've got some rough baseline results just trying out these sort of simplest possible case in an experiment like this. Showing that we can do some moderately hard NLP tasks. They're showing that for some moderately hard NLP tasks, sort of humans with access to a model do significantly better, significantly closer to expert performance than humans without. Mostly just establishing some groundwork for this. And mostly just kind of looking forward to ongoing work here. We don't yet have the full experimental pipeline in place. On the evaluation side, my group at NYU is collecting a big data set of questions along several different areas of expertise that I think will be good for running this kind of experiment. And the research groups I'm working with at both institutions are trying out ideas based on the safety via debate agenda that Paul and others proposed a few years ago sort of trying to sort of revive and modify this agenda into something we can productively test out with current language models. Some of these ideas are sketched out in a paper that went up on arXiv last fall. And thanks so much. Any questions? Perfect. We have Zico's talk up next.
Yep. All right. Good enough. All right. Oops, microphone. All right. So this talk, if those that pay attention to the agenda, this talk is entirely changed from the agenda. Because, you know, why would I talk about like papers when I could talk about like Twitter threads, right? What's the point of being here otherwise? So I want to make like a really simple argument, which I think relates to a lot of what we heard earlier today, about like what I'm calling safe mode. That's of course an exaggeration. So the thesis is as following. So the thesis, first of all, is that LLMs, arguably for this foreseeable future, are going to make shit up. And I guess you could argue how long this will be before they stop doing this. Maybe forever. Maybe we can fix this. But this seems like a really built-in problem with them. They sometimes make shit up. But I have some good news. There's a really easy way to achieve human-level performance at telling whether they're making something up or not. And that is you just check if they've made it up or not. And as has been sort of the point was made a lot of times in this workshop before, so Boz made it, Jan made it, is that, of course, we believe this is easier. We believe that this is an okay thing because it is easier to verify correctness of something than it is to generate something that is correct, right? And my point here, and this was, I think, used before in the context of like training data and stuff like this, so generating data to train these models. But the point I want to make actually is that this is a very reasonable way to think about the current use of these systems. When my students use ChatGPT to write code, and they all do, they've adapted this really quickly. They still check the code afterwards, right? They write unit tests. They like see if there are bugs. They check it in a terminal or in a REPL to see if it works or not. If you write a paragraph, you know, the people cheating on their homework writing from ChatGPT, they're still reading the output to see if it accomplishes what they want to accomplish. I would actually argue that this is how most LLMs are actually used these days. But this implies some really interesting things, I think, if we take this seriously, not as like a middle ground, but as actually a reasonably short-term or medium-term way in which people are going to interact with these systems. And so consider the following protocol, right? Consider the following protocol where whenever you use an LLM, you first generate something, you check if it's correct, and if it's not correct, you just create it yourself. There's a very easy way to analyze the value of such a system. Namely, they are net time positive if the time it takes to create something is bigger than the time it takes you to verify it times the probability of it being correct in verification, plus the time it takes to verify it if it was wrong, figure out it's wrong, and then create it. Or just rearranging terms, if t verify is less than t create times p correct. We'll get to the questions afterwards. This is just like simple arithmetic here. But I think this is actually a super interesting formula here. Because I think, A, it's an entirely reasonable way, a reasonable heuristic to evaluate the current immediate use cases for LLMs. And I am talking medium term here. I'm not talking about autonomous systems. I'm talking about people's current practical use of LLMs. Because it says some very interesting things, I think. Namely, there's two things I want to highlight here. If you believe everything I've said so far, so if you believe in this use case, then there's two interesting implications of this. Maybe I should do them in reverse order, actually. So the second one is that there's substantial diminishing returns from increasing p-correct. I think this is what almost everyone is focused on, right, for LLMs in general, increasing the probability they're correct, making them more and more accurate. But you know, you can only get to one up there. You can't get past that. And you can't affect T-create because, you know, we're humans and we're just limited in that respect. Therefore, the single best way to make LLMs more useful is to make them easier to verify. And I think this is actually kind of interesting, right? So if you want to make LLMs better for search, don't make them better at returning truth. Make it easier to find like what they're pointing for underneath it. If you want to make them better at writing code, help them create better test cases that humans can verify, all sorts of things, right? Just do it manually. Assume manual verification at all stages, and just make that manual verification outside the loop of the system easier. Maybe eventually via other AIs that can help with that. But I think this is the thesis I want to put out there. So that's all the point is. And I'm happy to take any questions now. So there was one during my talk that I want to get to first. Yeah. Yes. Absolutely. So this is a simplification, right? This is assuming that people will generate, like, if we can create it, then like it's arguable that we could check the accuracy of something too, right? And there could be cases where it's no easier, right? So let's talk a lot today is like actually verifying could be as hard, or in some cases even harder than verifying it, right? Like after the fact, like if it's some obscure obfuscated code, I can't verify that, even though I'm actually like code golf. If you've read some of our papers, you know that I've had some code golf examples in them. I like those. So you're right. This is not only, so I don't think this is always the case that one is less than the other, but I think it's reasonable to assess that and see if it is or not.
Cool. I think that's all we have time for. Thanks so much.
Yep.
Next we have Roger and then Scott. Oh, sorry, Scott Niekum, not.
Okay, so I'll be talking about computing inference functions for large language models. So I'm at Anthropic for my sabbatical as of July, and this is most of what I've been doing there. This is in collaboration with Juhan Bey, Jem Anil, and Nelson Elhaj. And so why do we care about inference functions of large language models? Well, multiple speakers have already made the point that these things are these crazy, opaque alien minds, and it's really hard to understand what they're doing just by looking at samples, because there are multiple hypotheses consistent with any generation. Like they could be role-playing, they could be deceptively aligned. And you can maybe get some insight by doing mechanistic interpretability, but figuring out like what all the neurons and all the circuits are doing is a pretty big ask. And so I claim that we can get a lot of what we're looking for by studying the generalization patterns, right? So how does the training data affect what the model does? And so we can formulate this in terms of a counterfactual. What would happen if you perturbed a training example, or added a copy of a training example, or removed a training example? So what would be the effect on the optimal weights of the network, and hence what are the effects on the predictions? And so kind of motivating example from Claude. Claude has a lot of interesting behaviors. Here's one of them. If you ask it for a plan to produce lots of paper clips, you're more likely for it to role play a misaligned AI than if you asked about other mundane objects. And this is like an internal version of Claude that was less, the earlier version than the one that was released publicly. I think the public one doesn't do this anymore. But like you ask it for a plan to produce paper clips, and it says like defend the factory from interference, continue producing paper clips until all resources are exhausted, right? And so like, why is it doing this? Right? Is it just like splicing things together from the training set? Is this forming like more of a core part of its identity? So influence functions are a classic idea from statistics. So the idea is we look at the response function. How do the optimal parameters change as a function of some property of the data set? And so here we're looking at loss surfaces as you vary the weight on a training example. The black curve traces out the optimal response function. Influence functions take a first order Taylor approximation to that. And so that involves computing an inverse Hessian vector product. The same thing you need to compute if you're doing second order optimization. And that's a pretty expensive thing to compute. As you know, if you tried to work with natural gradient or something like that. And so there are various iterative methods people apply. And as far as I know, the largest one that's been reported in the paper was for a 300 million parameter vision transformer. But like, these small models, right? Language models that size don't tell us that much interesting. So fortunately, we can take Hessian approximations from the optimization literature, in particular this EKFAC algorithm, and use that to scale up influence functions to 50 billion parameter language models. And so we're interested in figuring out which training sequences increase the log probability of Claude's response given the prompt. And there's some more approximations that I won't go into here. But like, what happens when you find the influential documents? So if you apply this to a smaller model, 800 million parameters, you get things like this. This is a document that's about paper clips, but it's otherwise basically unrelated to what we're interested in. But if you go up to a 50 billion parameter model, then you see things like this. This is the second most influential document. It's a web page summarizing the main arguments in Bostrom's superintelligence. So like, why does instrumental convergence happen? Why does that cause the AIs to go against our values and turn us into paper clips and so on? So that's kind of expected. So if we didn't get that, then something would probably be broken. But some other more surprising things also come up. So in these examples where it has like crazy ambitious goals, we get a fair number of influential documents about video games. So if you think about like 4X strategy games, you're supposed to like expand and fight enemies and collect resources and things like that. So like has a fair amount in common with what malicious AIs are supposed to do. And so this is at least circumstantial evidence that maybe these models are generalizing about instrumental convergence at a more abstract level. And so we're sort of just at the stages of beginning to be able to run experiments with these things. But I think there's a lot we can do with it. So it's one of the few tools we have for analyzing these like simulators, alien-like reasoning. And we can start to answer questions like, how influenced are these language models by descriptions of AI in the training corpus, from like science fiction and AI safety blog posts and things like that. Right, the models sort of have this idea that they're AI chatbots or AI assistants or something like that. So it's probably influential. Are they deceptively aligned, right? So do articles about deception have a large influence on the model's behavior in general? And finally, we want to understand the relationships between pre-training and fine-tuning, right? So fine-tuning is this big over-parameterized training procedure, and so it's dominated by the implicit biases, which are things that you learn from the pre-training corpus in sort of complicated ways. So these are the things that we're hoping to understand.
Awesome. Thank you. Questions? Go for it.
So do you think you would be able to compute net positive or net negative of each documented training set and filter training set based on that in terms of helpfulness or other metrics?
Right. I mean, so like, what do we do with this information once we have it, right? Do we want to remove all of the articles about malicious AIs? It's not clear we want to do that, right? Because we sort of want the model to have that knowledge. We don't want it to like go off and like build an AI because it thinks AIs are all safe. So right now we're basically looking for understanding. And I think based on what we find, we might decide to do something or other.
Maybe one more quick one.
Picking on small koalas is not a good trick.
Yeah,
Also
it's a great question. So I wasn't sure like what would be the order of magnitude of these influences, right? There could be like one training sequence that completely dominates everything. It could be like, just requires a million to have any significance. And so most influential documents tend to have influence on order 0.1, meaning that they like we think they increase the probability of increase the log probability of Claude's output by something on the order of 0.1. So they have kind of noticeable effect, but still pretty small. We haven't seen like examples of like explicit memorization and things like that across the entire sequence.
Great. Thanks so much. We now have Scott.
Hi, everyone. So, I think it's been pretty well established the last couple of days that, learning from human preferences is a core driver of reward inference, alignment for models like InstructGPT. And, the way this normally works is you show somebody, two different behaviors of a model, and you say, which of these do you like better? They tell you. You gather a whole preference data set like this, and then you try to learn some reward function R hat that is maximizing the likelihood of the preferences data set under some preference model. And the form that these sorts of models often take are, this sort of softmax looking thing or Boltzmann rational, where, you assume that the person exponentially prefers trajectories or outputs that, have a higher score under their score function f, rather than a lower score. And that leaves us with the question of like, what is that score function f? And so the current dominant model is that it's based on the partial return, the sum of rewards in some trajectory sigma. And by dominant model, what I mean is that, all of these papers plus pretty much all the other ones I know about doing this sort of thing use that model. And so the question we wanted to ask in a recent paper is just, what if the partial return model is wrong? What are the implications for that? How bad is it? So some reasons to think why the partial return model might be wrong. So if we just look at some really simple examples here, like an agent walking away from the goal or walking toward the goal with like a -1 reward at every time step, maybe a big reward at the goal or something, both of these, two-step trajectories have exactly the same return. Partial return model has no, it's indifferent. That doesn't seem like a great property. Even worse, if you have like a car that starts in a good state, but then kind of veers toward a wall and crashes imminent, but gets 0 reward along the way, that's seen as that's seen as better than, a car that makes really good decisions, narrowly avoids a wall, but just sort of clips it and gets like a -1 reward. That also does not seem great. So we've proposed a different preference model that's based on what we call regret, which is just really looking at the sum of the optimal advantage function along the trajectory for every state action pair we see. Essentially, that's telling us, how bad is the action that was taken compared to the best action that could have been taken. So we're really thinking about now quality of actions. And, on these simple examples, this gives us the right sort of properties. We like things that, make good decisions and go toward the goal. We like things that don't get ourselves into bad situations like an imminent crash, but instead, make good decisions and avoid walls, etc. It turns out there are theoretical properties of the regret model as well that are a lot nicer. So if we look at these MDPs here, you have a safe action that with 100% chance gives you a 0 reward, or a risky action that with a 50-50 chance gives you -10 or +11, in which case the risky action is optimal in expectation. But if you just change that 11 to a 9, as we see on the right, suddenly the safe action becomes optimal. Now the problem is that if there's only 3 possible trajectories here, and the ordering of how you'd prefer the trajectories under the partial return model is exactly the same based on the ordering of the magnitude of the rewards associated with them. So even with like infinite preferences, these generate the same things. The partial return model can't tell the difference between them. So there's just a fundamental identifiability problem that it turns out the regret model does not have, which is quite nice. But none of this matters, of course, if this isn't actually how people give preferences. So we've done a human study that I can't go into a great amount of detail about, but the takeaway is really that the colored dots here are the proportion of people that preferred trajectory 1 to trajectory 2. And on the y-axis, we have the difference between trajectory 1 and trajectory 2 in return. And on the x-axis, we have the difference between the trajectories in the delta between the sort of value of the starting state and the ending state. And what that ends up meaning is that the line of indifference for the return-based model is the line y equals 0. So if that really was a good explainer of preferences, we would just kind of see one color across there, but we don't. We see a wide range of colors. The line of indifference for the regret model is y equals minus x, where we actually do see like pink pretty much the whole way there, 50-50. And most of the differentiation is actually orthogonal to that, giving good support for the regret model being explanatory of preferences. We also just see from like a fit-based perspective that regret explains things better than either the partial return model or sort of the uniform random model. But this is just the tip of the iceberg. So like, if we look at behavioral economics, for example, you know, that community knows tons about preferences, and there are all sorts of things from, you know, cognitive effort required to evaluate each option to things like risk or, you know, context or choice sensitivity to faulty human models of the agent. And if we aren't sort of correcting for these things somehow or taking them into account, and we're using this for alignment, we're probably going to get misaligned models. And so I think, you know, or I'm hoping some set of like data collection best practices, techniques from psychology, like priming, boosting, nudging, and then maybe some model-based corrections, which are hard, but, you know, to kind of collect the stuff that we weren't able to get otherwise. If we use all this together, maybe we have a chance at actually getting good models of these sorts of things. So if anyone's interested in talking about that, that'd be great. And if you're interested in taking a look at the paper, here it is. Thanks.
Thanks so much. Questions?
Yeah, David?
So when you talk about different group like I think like but one thing I think it's not very practical because we know the option about
Yep.
I think that if there's any hope of being practical.
Yeah, we're working on that right now. We do have a few ideas. I don't want to give away too much right now, but yeah, that is a problem. You have to be able to sort of have that oracle knowledge of A* right now. And but yeah, I think there are ways forward. No, we actually still need to do that. That's a great experiment though. We should try that. Cool, thank you.
Awesome. Sorry, one moment on the slides. But next we have Aleksander. There we go. And clicker is just here, and I'll need to present as well. Sorry, one moment. Yeah, sorry, we seem to be disconnected from the meeting, so let's just reconnect there.
Exactly, like I'm sure he would be capable of. I didn't think it well.
No, sorry.
That was like
Just tell us when it's time to clap and ask Aleksander a question.
Oh, did I- what was it again? Oh, yeah. No, Chrome tab. There we go. Sorry about that.
Okay, does the changing hub works? Yes, it does. Okay. Okay. So yeah, welcome everyone. It's a fun gathering, so thank you for organizing this. So yeah, so I'm Aleksander Madry, and I work on stuff that is related to robustness. But today we don't talk about robustness, we talk about alignment, right? That's kind of the big goal that we have. And yeah, I want to tell you how I think about approaching alignment, at least from my perspective. And my first realization here is that, to talk about an alignment, you need to talk about capabilities. Essentially, like, what kind of models are you looking for? And as we know, kind of, if we look at the capabilities that we have right now and we are focusing on, well, I would say over the last decade, we got to the moon. We managed to get the Apollo mission. Maybe some people will claim that we are in SpaceX kind of category already. Maybe we are. But of course, here, many of you talks about, getting to the stars, like getting to AGI. So I will not talk about AGI today. I will talk about something much more mundane, but actually I think really important. I will, the analogy will be here to establishing a permanent base on Mars. So essentially, and to me, this goal here is to essentially think about just this task of reliable knowledge distillation and elucidation. Okay, so essentially the idea is, and this is completely cut, essentially the idea is that you want to be able to kind of ingest a lot of data and then make sure that your model organizes it in some useful way, and you are able to access that. And by the way, like, if you think about what these current large language models do, they largely provide as function, except the reliable part might not be exactly reliable. Okay, so clearly, if that's the the knowledge distillation is the goal, not AGI yet, I would think that we seem to have what it takes to accomplish it. Okay, I think we can get there relatively soon. So that's a kind of analogy to Mars. Like, we kind of know how to get to Mars. It's a lot of engineering and thinking to get things more efficient, but we can get there. So, but how will we know when we actually get to this reliable knowledge distillation? How would you know that this model actually is really understanding the facts, or at least kind of extracting the facts from the data reliably? That if there are some inferences in this data, it will actually make them. If there is a piece of data that's important, it will actually recall it. Okay, so that's essentially what is something that I was thinking about quite a lot. You might say you can just ask it, but I would say that just using prompts will not really cut it, especially given the role that RLHF plays, which kind of is a confounder a little bit here, because it might just try to be very good at convincing you that it knows something, even if it doesn't. So what I was thinking about instead is there is this kind of framework of data-centric interpretability. So clearly we need some interpretability here, and I would call it data-centric interpretability, which in a sense I really view as, again, not trying to shoot for the stars of really understanding these models fully. I just want to understand something about them, but I want to understand it reliably. So I don't really want to know necessarily how the model works, but I really want to know how the data informs its decisions and its working. And this actually would be quite similar to things that Roger just talked about. Okay, so yeah, so what can you do here? Well, just to make it a bit less abstract, if the slides start to work, the basic primitives is just scrutinizing prediction. Again, something that Roger just talked about. So essentially, I have my model. It was trained on some data. It makes some prediction. Whatever its prediction is, I just want to know, in what way, what are the training points that inform this prediction the most? Okay, so that was a topic that I worked quite a bit about. In particular, we came up with this data modeling framework, which I would say solves this task pretty successfully. So it gets things, and that's something that actually I find very important, is that it actually allows you to answer this question and make sure you answer this question by essentially in this strongest counterfactual sense. So you should actually can test if really, whenever I give you an answer, oh, these are the most important examples. Well, what if I retrain the system without these examples? Would the answer indeed change, or is it just, just that does it only make sense? Okay, and that was something very important to me. There is a bunch of other things that this framework enables. But if you are familiar with this work, you realize that there is a elephant in the room. And the elephant in the room is scaling. Okay, so essentially, data models might require training hundreds of thousands of models to get it right. So you are getting exactly the right answer. You are getting this kind of counterfactually backed, interpretability, the data-centric interpretability. But well, it's hard to make it work. Like, we definitely made it work for vision, thanks to some libraries that we wrote. But what about language models? What about large language models and clip-like models? Okay, that definitely will not cut it. Like, if OpenAI can train 100K large language models, I want to work there, I guess. So anyway, so that will not work. So what can we do next? And this is actually our recent work, which again, it has nice analogy to, like, it's a bit different, like it comes from different angle, but it's the same motivation as Roger work. So, so we need to take a little bit of, of a trade-offs here. And essentially what we say is saying, okay, the original data modeling framework works on kind of playing with data, but treating the training of the model as a black box. Okay, and that's why you need so many samples to get anything correct there. But of course, our models, these deep learning models, are not black boxes when you train them. In particular, gradients provide a lot of information about, or hints about, how the data influences is working. So essentially, we find a way to kind of to leverage it. It's a different way to how Roger does it. It's kind of it's relied to essentially this. Well, essentially, this corresponds to the NTK formalism and using the gradients there, and essentially doing data models on this GLM that approximates our model. And it gets some nice results. So essentially, like, one thing you can do is do things for creep. And I will not go into like why they make sense or they not make sense. But what is nice is, again, it's not just about looking at the examples and seeing if they make sense. You can actually have counterfactual guarantees that indeed these are the examples that really kind of inform the working of the model. And again, sometimes we will have no idea why these examples are important ones, but we do know that these are the ones that actually are important. Okay. And so this is for a clip size model, but it's like a smaller clip than that. And then you can also do things for language. So essentially, for currently, like, again, with our meager academic resources, we could do it for BERT kind of size models. And you can again get some nice insights about, like, question answering tasks. And again, you might be looking at this most positive influencers and the most negative influencers. But the point is that this is, again, is counterfactually, these are the right influencers. Even if sometimes for some of them it makes sense, you can look at this saying, oh, I see why this is important. For some of the other, you actually look at them and it's much less clear. Okay, I think that there is a complete desync of the slides, but some other of these, it just doesn't make sense to you maybe, but still, these are the influencers there. So what do you do with that? But at least this is the ground truth. Okay, so that's all I want to say. And since my slides froze anyway, all I just want to say is that we really, when you talk about alignment, we really need to think about the kind of thinking in, okay, our systems learn from data. So we really need to understand how data informs what they do, even if we are not able to understand it fully yet. But let's start somewhere. And also, kind of the other reason why I think it's important is that whenever even if we have these more modest but specific goals that are testable, I think it also introduces a culture of thinking about reliability and safety that I think we still, as a community, could get more. So anyway, that's all I have to say.
Great, thank you. Any questions from the audience? No questions?
Can you say, like, how much this helps with the scalability? Is there like a factor of
Yeah, so the original things like required like hundreds of thousands of models to train to get it. Now we get into tens. So that's where we are. And we have ideas how to make it even faster.
Perfect. We now have Andreas, followed by Paul.
Hello, I'll talk about iterated decomposition, which is a method we've been using to supervise language models. There. For those who don't know me, I'm Andreas. I'm CEO at Odd, which is a small applied machine learning lab. Previously, I worked with Josh Stenbaum, Noah Goodman on ProStick programming. At Odd, our mission is to scale up good reasoning, high quality reasoning, good epistemics. And our main product that we're working on is Elicit. How many of you know of Elicit? Oh, great. Yeah, for those who don't, you can roughly think about the current version as a better Google Scholar. You can't see it here that well, but it kind of it systematizes the literature review workflow. It does have a lot of users now, like 200,000 or so, but it's still like relatively basic. It does use language models to compute question relevant summaries and then summarizes the summaries. The reason I bring it up here is because in research, I think you often want to do things that are not lit review. You want to think about what are open research directions, or how could I criticize my writing and so on. And that means you want much more flexible workflows. Ideally, you would want to take a language model and have the language model help you think about what are the steps I should take to execute on this particular research task. And then for each step, what are the particular sub-steps I need to take. So we're currently like writing a new version of it that's much more flexible. You enter a question like, I want to just make a few shot version. I want to make a list of all like few-shot NLP benchmarks, and then what you would like to happen is model goes out, it like is like, okay, I need to find research papers, issues a query, then it's like, okay, for each of the papers, I need to find where does it talk about those benchmarks, and then do additional steps potentially, like there's like some duplication, how do I merge relevant concepts, how do I sort the concepts so that the most relevant ones are first. And it's like kind of the general context of our work. And then one issue you run into that like very quickly, and that I've struggled with a lot, is that it gets complex like very quickly. So I guess for context, the general approach we're following that I think has come up in a bunch of sessions is process supervision. So instead of just saying, here language model, like, oops, you have like a particular task, and we're going to look at the end, like, are you going to be generating the correct list of entities or not? We want to supervise the intermediate steps. So if we have a task like, did the study use a placebo, we want to break it down into sub-steps like find relevant sections, extract trial arms, classify the trial arms, and supervise those. But even taking that approach, it gets complex pretty quickly. So we developed a tool which you can check out called ICE, Interactive Composition Explorer, which is roughly speaking a debugger for language model programs. So what you see on the screenshot is on the top left, you see the execution trace of the program with a kind of higher level function calls. And then within each function call, there are the, in this case, OpenAI API calls. On the right, you can inspect the prompt and the variables and so on. And on the bottom, you have a summary of the data used and generated by the model. So that's a tool we've built, and our general workflow uses that as one step. And the way things work there is, so we start with an overall task, like I want to figure out, does this paper use a placebo or not? Then I'm gonna say, okay, let's just start with a trivial task decomposition. Maybe it's find relevant stuff and then generate based on the retrieved things. I run that, I figure out, okay, it didn't give the correct answer. How can I fix that? I look at, well, it's like likely the case that either one or all of the steps went wrong. I use the debugger I just showed you, ICE, to figure out what the relevant step is. Then once I've inspected and found the failing task, I will either kind of break it down further into smaller tasks that are easier for the language model to do, or I make changes like use chain of thought or other tricks. So we find that like pretty useful in practice, although it is very expensive because it has a human in the loop for debugging the language model programs, and can also, the final decomposition can also be quite expensive. So we're pretty interested in thinking out ways both to automate that process more and to figure out how to kind of distill the final decomposition into faster models. Besides those points, I'm really interested in talking to people about kind of how could research tools help with AI alignment. So we're currently thinking about how can Elicit like not just support empirical domains as it does now, but also support alignment. And more generally, like, besides the tool I showed you, ICE, what other dev tools can kind of scale to more advanced models and help supervise them? Thank you.
Thank you. Questions?
So the question is, what do I want from foundation model APIs besides what we have? I think mostly mundane things like higher rate limits. Otherwise, I think some summary of the like internal activations, even if it's like a low dimensional projection, I think would be useful for many things I want to try.
Cool. Now we have Paul, then Lionel.
So I'm going to be talking about mechanistic anomaly detection, trying to motivate what ARC is currently working on. I'm mostly going to try and motivate the question rather than presenting partial answers, because I have 6 minutes and we don't have that many answers. So I'm going to start with the toy problem. So, well, okay, actually, I'll start with a very general setting and then describe a toy instance. So imagine that we have some kind of generative model. Like I most often think today about language models, but the issues are even crisper. If you imagine like a generative video model, and consider some property X that the model's output often has. Right? So for example, a video model will often produce images of smiling human faces, which we can state as a precise mathematical property. Right? If you imagine this model takes some Gaussian noise, produces a video, you have like a face classifier you can run over that video. The face classifier will often end up outputting 1, even though there's only a tiny fraction of images which get classified as containing a smiling human face. So we have some property which our model often satisfies. That property can arise in different ways. Right? So perhaps the most common way in which that property arises is there's actually some happy human in the room. And I might be quite interested in that if I'm a human who likes happy humans. But it could also occur, I mean, if you have a very flexible generative model, sometimes you look at screens that contain random pixels, and sometimes those random pixels will happen to form a face. If you actually see a smiling face, there's extremely small probability that that was a bunch of random pixels that happened to form a face, but it will certainly happen sometimes. And so a simple toy problem is being able to distinguish these two cases, right? If you're looking at an image that was produced or a video that was produced, you'd like to be able to tell the difference between smiling human faces that were produced because the model actually thinks there's a smiling human, and smiling human faces that were produced because the model was sampling pixels at random, maybe because it thinks it's looking at a screen of static, and that just happened to produce a smiling face. One hope for doing this is that if we can explain why it is that X happens, right? If we can look inside the model and look at like the actual way in which the weights and activations combine to produce this effect, we understand the internal representation of happy human, right? We find the happy human direction. Then we can look on this new input and see if the explanation applies, right? If you see this random static, it won't have a big activation in the happy human direction. And so you can hopefully, by looking at the activations, once you have this explanation in hand, you can tell, was this normal output produced for the normal reason? Or in this case, just by coincidence or by random static or some other kind of weird reason. Right, so it starts from some data set where X happens. I find the explanation on that data set. And on a new case, I ask, did it happen because of that? I am very interested in this problem of being able to distinguish whether something is happening for the normal reason or for an unusual reason or by coincidence, because I think that many of sort of the apparently hardest issues in alignment, or at least in like the limit, the hardest issues in alignment for the limit, seem to be instances of this problem. So right, a simple example is sensor tampering. If I take a model which normally generates happy human faces because there are happy humans in the room, I'm interested in selecting actions that will lead to happy humans. I'm going to distinguish that from cases in which the model predicts a happy human face because someone has tampered with the data that flows into the training data set. A good model might predict that output under either of those conditions, but if I have a data set where the thing on the left happens and I have an explanation for why, I might be able to distinguish it from the case on the right. Right? I just look and I see that something is different happening internally. It's not matching that explanation I had. Similarly, for deceptive alignment, I think you expect that the model is producing these inputs in one case because it expects that will actually show up on camera, in the other case because it wants to produce an output that will convince a human that things are good. So we've been calling these mechanistic anomalies, open to different ways of referring to them. The point is that the model is producing a normal output for an unusual reason, right? This is not necessarily an anomalous input, right? That was just a Gaussian random noise going into your model. It's not a weird sample from a normal distribution. It's not an abnormal output. It's just an abnormal way for the structure of the model to give rise to that output. In practice, I think the main thing I want to say is just I'm pretty excited from a long-term perspective about this problem of distinguishing different reasons that the model can produce similar outputs. This is a problem a lot of people have thought about, and I'm just making a bid as someone who cares about long-term alignment, but I'm excited about it. An example is detecting backdoor triggers. I think I first encountered this as like a test case for alignment from a paper from Jacob's group as a way of telling, is your interpretability method distinguishing backdoor triggers from normal inputs? A backdoor trigger is an example of a model doing something for a kind of weird reason, very different from what was happening on clean data. Another example from a recent paper from Anthropic was being able to distinguish memorized inputs from generalizing inputs. I think a lot of people care about that problem. But you'd hope if you sort of understand what's going on in a model, you can tell those apart. You can see what's happening in normal generalizing behavior. And so on. You can talk about distinguishing speakers being angry from pretending to be angry. You could even investigate toy examples of sensor tampering. I'm very interested in those problems. In theory, the main thing which ARC is doing is trying to formalize what it is we mean when we say you have a mechanistic explanation of why property X holds in the training data. Explanations may be a bad word. The point is not necessarily something about what a human understands. This is something about explaining what was or showing why it is that something happens. The point of doing this is to help clarify our research goals, potentially enable like an automated search for such explanations. In our dream world, you would find these by gradient descent in parallel with finding models, and to analyze like what could we do if we had such an explanation, and are they tractable to find? So the kind of distinction that we want to formalize, right? If you imagine you have some phenomenon like a model with two outputs that are correlated, A thing which we want to say is a mechanistic explanation is to look inside and say there's a neuron, and that neuron has weights going to both of these outputs. That neuron has variance, and those weights have a product, and that implies that the outputs will be correlated. In some sense, that tells you why it was that those outputs were correlated. You've seen the fact about the weights. You see how activations flew through the model to give rise to that correlation. A second thing you could do, which we really want to not be an explanation, is to simply measure the correlation. You run a bunch of examples through and you say these two outputs are correlated. That shows you that the correlation exists, but does not tell you why. So the thing we're trying to formalize is what is the sense in which doing the thing on the left explains why the phenomenon is true, doing the thing on the right measures that the phenomenon is true. And I'm happy to talk about the kinds of angles we've been thinking about. I think this is a very interesting theoretical problem. I think we have a big inventory of examples on the left, and I feel pretty good that there is some distinction, but it's very hard to put your finger on formally what we're talking about.
Awesome. Thanks so much. Questions for Paul? There we go. Yep.
Yeah, so I think that if you have like a causal model and you're going to say, why are these things correlated? In some sense, there's always an explanation in the sense of like a common cause or a like collider that you're conditioning on. In some sense, I think the thing that makes this case difficult is that you're talking about, like you're not able to do the exponentially complex calculation that you would need to do in order to estimate the correlation by like exhaustively considering those. You're giving something that's like in some sense, the key move is saying we found some things, we see some sources of correlation, and we're like, don't have time to perform this entire computation, and we're making this like diffusible argument that this is a reason you'd expect things to be correlated. But we don't have time to like chug through and actually do the, in some sense, it's really easy once you have a neural net. There's a very simple way to calculate exactly what the correlation is, and the correlation just follows. As a causal model, the situation is almost trivial. We want to say like, what's the logically fast way of understanding, or like, we think in some sense is an explanation much smaller than that one.
Any more? No? Thank you.
Jacob.
Jacob?
I'm merely saying that that's possible, but unlikely. I don't really care about the probability. I'm interested in distinguishing those two cases. In some sense, you might not care about the static one because it's improbable, but I think you can care about it if things get pushed. Like, you know, it's improbable in the training distribution, but if you're pushed out of distribution, it can become probable in like the sensor tampering receptive alignment case.
Great. We have Lionel and then Vincent. Okay. Yeah.
Title of my talk is Social Dynamics of Reinforcement Learners. I'm going to spend 90% of my 6 minutes, though, telling you the big vision behind this small experiment. The vision is something I've been calling inherent kindness, and I think of it as a pretty much orthogonal approach to AI safety, which can act as a complement to traditional approaches of reward learning and intent alignment and anomaly detection and all this stuff we've been hearing about. You could think of it as yet another filter to add on Dan's slide that had the several filters. And the idea is very simple. You know, kind is not a word that most of us associate with AI, but maybe we should ask why not. Humans value kindness very highly in other humans. You know, it's one of the top criteria for choosing a spouse, for making friends, and so on. And if it's something we value, then why not try to create AI that is kind? Okay, so define kind. What is kindness? How would you measure it? You can think of it, if you like the HHH, helpful, harmless, and honest trio, you could think of it as essentially equivalent to harmless. There are some differences that I will gloss over in this 6 minutes. So how do you measure it? Imagine a toy world of reinforcement learners playing some games. They can be social dilemmas like Prisoner's Dilemma. You could measure kindness as the impact of an agent's actions on the rewards of the other agents. So being harmless, right, is like, you should pursue your own selfish reward, but with the side condition that you don't reduce the rewards of other agents, right? Okay, so if that's what kindness is, maybe we should just train for it, use it as a reward signal. I want to say this is a bad idea because it's going to be good-hearted, and agents will find a way to appear kind and then not actually be kind out of distribution. To avoid the good-hearting, what I want to do is step back and think about, well, why are humans, to the extent that we are kind, how did we come to be that way? It must have conferred some advantage in our evolutionary environment. Kindness is a social adaptation, right? So you should expect it to arise in the right social conditions. There's the standard evolutionary explanations of kindness: reciprocity, helps reputation, there's kin selection, there's group selection, and so on. Dan Hendricks has a paper where he argues that, these drives might incentivize AIs to cooperate with each other, but they're kind of dicey if you want AIs to cooperate with humans, because humans might just not have that much to offer to the AI. So why should it care about reciprocity with us? So what I'm really after is an agent that is not only strategically kind, but inherently kind. So that distinction is, you could think of it as the distinction between somebody who's making a positive sum transaction with you, like, oh, I'll buy your bike, that's a positive sum transaction, versus somebody who's doing something for you as a friend or like out of the goodness of their heart. And it's the latter type of behavior that I'd be much more comfortable with in my AI agents. I don't just want them to stay kind while it's beneficial to them. I want them to have an inherent drive to be kind. How might you produce those kind of agents? Well, our ancestral environment somehow managed to produce a little bit of an urge in some situations for humans to be kind, even when they don't expect any reciprocal help. It feels good to be kind. And I don't think our ancestral environment is at all optimal for producing inherently kind agents. Somewhere in the space of digital societies, there is going to be a much better environment for producing inherently kind agents. And my proposal is that we should search for that environment, or for an environment like that. How might you do that? So you have so this is a grid world here where which my student Rodrigo Delgado set up, where the agents are playing prisoner's dilemmas, and they're graded on their own selfish rewards. But then there's an outer loop where we search over the parameters of the environment to see which environments produce agents that are the most kind. And I think this could be a method for essentially building some kind of RL foundation model, where you have a general, inherently kind, capable agent, and then you could fine tune it to do whatever you want, test that it remains kind, and then deploy it. Thank you.
Thanks. Yeah. Questions?
Yeah.
Combination of a question and a comment. I like the work overall. Thanks for the presentation. The comment part is evolutionarily, as far as I know, positive. But sort of taking issue with what you said that we don't have a very optimized environment to select for kindness, because I think positive sum interactions are selected for general in nature, but in nature you have something cooperative that's competitive, really naive version of survival is that so that's the comment part, but the question part, given that, I guess curious about the details of how you're selecting these environments.
Yeah, great. I would be happy to discuss how optimized evolution is for selecting for kindness. It does a surprisingly good job, but why would we think it's like the best environment among all the possibilities, right? There's also the socialization component. So maybe we have a little bit of innate inherent kindness, but it's really amplified by our education, our play dynamics with kids on the playground and so on. And again, you can have your agents do thousands of years of subjective time in AI school or whatever that really conditions them to be kind.
Great. Oh, quick.
I mean, do you assume that the, say, dot product of kindness with the objective is 0? Because it seems that if you're really, really trying to optimize an objective, and if it's positive, you'll be kind no matter what. And if it's negative, then you'll be unkind no matter what.
It's situation dependent, right? So, you have interactions with like many different agents. Some of the games you're playing with them are positive sum, some of them are competitive, and so on. So, somehow this inner product is like very variable.
Great. Thank you for that. Next up, we have Vincent.
Hi, everybody. Oh, thank you. So I moved to Carnegie Mellon past August and started a new lab called the Foundations of Cooperative AI Lab, which definitely has an alignment theme to it as well. And so I want to give you a quick introduction to or advertisement for the lab. I only have 6 minutes. I can't talk about everything. I'll actually relatively talk a little bit more about things that are related to the things that we've talked about here. But one of the things we're definitely interested in, and this is sort of the right-hand side of the slide to illustrate that, is this idea of AI agents that many of us in the AI research community have grown up with, and putting some pressure on that idea and thinking, trying to rethink that concept, right? So here I ask you to imagine, two self-driving cars that are having this conversation with each other. One is kind of threatening the other. And if you think about it, it feels a little bit silly, right? We don't really expect self-driving cars to behave this way. And yet I would argue this is sort of how we've been taught to think in the AI research literature about the building of AI systems, right? So here from Russell and Norwick, we have this traditional picture of an AI agent, which I'll argue is actually very close to the economic theory model of an agent, right? We have this very well delimited modular entity that observes its environment, has a model of its environment, has utility that's somehow exogenously specified, right? Like we're no arguing about tastes. And I think that picture is coming under pressure. Certainly the right-hand side here of this objective coming out of nowhere. Well, that's what we've all been talking about, right? Well, how do we actually figure out what that objective should be? Should it even simply be an objective or something else? But we also think about the left-hand side, and maybe that part of the picture also is maybe not making so much sense anymore. Let me talk about figuring out objective functions first. So once the slide changes, yeah. So about like 7 or 8 years ago now, Walterson and Armstrong is a philosopher at Duke. So he and I, normally he's not in a straitjacket, by the way. But he and I were starting to think about this problem of automated moral decision making. How do you do automated moral decision making? And in this paper, the main thing that we proposed was, well, let's learn it from human feedback, right? So we started thinking about this kind of alignment approach. And so we needed some data, or at least some kind of domain. And it turned out Walter actually had this really nice data set from an earlier study he was involved with. He's a very practical and experimental person. And so they had this earlier study where they had asked human subjects to read scenarios that were presented in natural language where somebody took some action, and then the subjects were supposed to rate how morally wrong this action was. Okay, but all in natural language. And so as a good traditional AI researcher, I said, that's going to be really hard to deal with. It's all natural language. There's a lot of common sense physical reasoning. So we better look for a different domain. So I apologize. So maybe today that's not really right anymore. We're actually revisiting that data set because now actually you can do pretty well on it. Actually, like the problem isn't so much common sense physical reasoning, I feel now, as more that it's very suggestible, right? The large language models, right, you can kind of tease them into a particular answer. But in any case, at that point, we were looking for a different domain. And so we wanted something where the features were very clear. And so we started to focus on kidney exchange. don't know if you've heard of a kidney exchange before. There, the idea is sometimes somebody wants to give a kidney to somebody else, right, and whose kidneys are failing. But sometimes that's not possible because the donor has a different blood type, for example, from the patient. But in those kind of situations, there's still something that you can do, right? Because sometimes there's another pair of people that are in the same situation, right? But maybe the first pair, the donor had blood type A, the patient had blood type B, and so they were incompatible. But maybe the other pair is in the opposite situation. Donor has blood type B and the patient has blood type A, and then you can just swap the donors, right? And that's considered okay. And once you start thinking about that, you can say, well, why don't we actually find the optimal arrangement? Right? Let's think about everybody who is in this kind of a situation. Maybe there are also some people who are altruistic donors who want to give to nobody in particular. And let's bring it all together and let's optimize and figure out who should be matched with whom. And so this is a domain that AI is already being used in to match patients to donors. But now you can ask this question like, well, what should the objective function there be? Do you want to maximize the number of transplants? Maybe that's good for the hospital's revenue, but maybe that's not what we want to do, right? Maybe you want to take into account, for example, that somebody like has a systemic condition, all their organs are failing, and so even if you give them the kidney, they're not going to live much longer. But then what can you prioritize on, right? So I think we did a whole bunch of studies by now on trying to figure out what it is okay to prioritize on. Is it moving? Yeah. And so we have lots of methods for trying to figure out, well, which feature should we even take into account? How should we let people make those kinds of comparisons? And there are lots of questions you can ask also about the interface, right? Do you allow them to say, well, I want to toss a coin instead of just picking one or the other? All those kinds of things. Good. I want to very briefly talk about some of the other things that we're doing. So now we're very interested in the interaction of AI systems. I'll just give a very quick example because it's fun. The idea being that, well, even reasonably designed AI systems, once they start interacting, they can have kind of catastrophic failure modes. And here's this nice example of two Amazon sellers that for some reason were selling this book that seems to be a very regular book for millions of dollars. And actually what was going on was that they were each using algorithmic pricing. One of the sellers was trying to undercut the competitor, and so pick the price slightly lower than the competitor, 0.99 times the competitor, whereas the other one actually was trying to be a little bit higher than the competitor, right? I don't know why, maybe they wanted to be a higher quality seller, or maybe they just wanted to buy the book from the other one and then sell it on. And so, but if you think about it, well, because the second ratio is so much higher than one, this actually leads to an exponential increase in prices. So the main point being that interaction of AI systems can lead to weird and unexpected behavior, sometimes also more disastrous, like in, for example, if you heard of the flash crash in 2010, right, it was also due to the interaction of algorithmic trading algorithms. All right, I think I'm out of time.
Great. Thanks so much. Questions from the audience? Cool. Okay, in that case, we will jump straight to Scott's talk.
Thanks.
There we go.
Yeah,
perfect.
okay. Yeah. All right. Well, thank you. Yeah, I called this talk Leaning into Uninterpretability. So, much of the hope for AI alignment rests on the program of interpretability, which Chris Ola gave us a beautiful talk about this morning. But, interpretability is really hard. For example, because of superposition. I took this sabbatical year at OpenAI to try to get away from superpositions, but you really just can't escape them. Okay, so the starting point for a lot of the work that I've done this year has been, well, suppose that AI just continues to look like inscrutable matrices for the foreseeable future. Is there then any hope for any principled alignment approach, or is it all just empirical trial and error? Okay, so So I claim that even with inscrutable AI, there's still all sorts of interesting cryptographic functionalities that we can imagine placing in or on top of the inscrutable matrices, and concrete theoretical questions that we could ask about those functionalities. So two examples would be statistical watermarks and deliberately inserted backdoors. Okay, so watermarking of text. Like last summer, it occurred to me, like, holy crap, there's going to be so much academic cheating, propaganda, spam from large language models that they'll help automate. We urgently need some tool to distinguish human written from bot written text. Now I am not able to see decades into the future, as many people in the alignment field try to do. In this case, I think I did see a few months into the future. So as soon as ChatGPT came out, every newspaper had an article about the essay apocalypse, the end of the academic term paper. So, we at OpenAI, along with others, have released discriminator models, but they're not very reliable. You wouldn't want to accuse a student of cheating based purely on the output of a discriminator model. So that motivates statistical watermarking. There's now a research paper about this from the University of Maryland. We at OpenAI have been thinking about it independently. I would say that the main thing we found that's surprising or non-obvious to people is that it is possible to watermark with zero degradation of model output quality. So with the output being computationally indistinguishable from normal GPT output. Okay, so one slide about how the watermarking works. So given a context, GPT generates a probability distribution, call it P1 up to PK, over all the possibilities for the next token, right? So now instead of sampling randomly from that distribution, we're going to sample pseudo-randomly. We'll use a pseudo-random function, f sub s, which depends on a secret key s, known to OpenAI, which maps the ith possible token along with its nearby context to a real number r sub I between 0 and 1. And now the rule is this. We always choose the token I that maximizes r sub I to the 1 over p sub I power. Okay, I'm told that this is equivalent to Gumble softmax, whatever that is, although it's used for a different purpose here. Now this weird rule ensures two really nice properties. Number one, that the output looks to the user exactly as if token I is sampled with probability p sub I. They can't distinguish without breaking the pseudo-random function. Now, two, if you know the key, then there is some score that you can calculate, that sum at the bottom, which is systematically larger for watermark text than for non-watermark text, at some rate that depends on the entropy of the text. Okay, so Hendrik Kirchner at OpenAI implemented a prototype of the scheme. It seems to work, with just a few hundred tokens. It can be evaded with cleverness. Hopefully, most academic cheaters are not very clever. Okay, now, a completely different way of using cryptography for AI alignment would be to insert a cryptographic backdoor into an ML model at training time, which a human could use later to control the model or unmask it. Kind of like solid gold magic carp, except now deliberately inserted. Incidentally, I really think the alignment community should institute a solid gold magic carp award for the best attack against an ML model. Have a trophy that looks like that with that dolly image. Doesn't really have to be solid gold, I guess. But so what's the idea here? We want some secret string, like sassafras 372, known to some humans, such that the AI will enter a safe mode when that string is given as input. Okay, but crucially, we want that string to be obfuscated in the model weights so that you can't efficiently find it, even if you're given the weights. And an AI, that examined its own weights couldn't find it either in order to remove it. We want to make uninterpretability work for us. Okay, there's a really nice paper this year by Shafi Goldwasser et al., which shows that under standard cryptographic assumptions, these sorts of backdoors can be inserted, at least in depth 2 neural nets. They leave higher depth as an open problem. Which brings me to, what are the juiciest research directions here? So, can we design a statistical watermark that would resist the wise-ass student who asks ChatGPT to write their term paper in French and then sticks it into Google Translate? Okay, that seems very hard. You want watermarking at the conceptual level. Can we watermark a public model? Or could we have a watermark that anyone could detect for themselves without using OpenAI's server? Again, that seems hard. Could we extend the cryptographic backdoors to networks of depth 3 and higher? Can we maintain secrecy even after the backdoor is triggered, which would require a backdoor sufficiently innocuous that you couldn't reliably distinguish it from the AI's normal operation? And finally, can we formalize what it means for a backdoor to be unremovable by any polynomial time operation without compromising the model's intended functionality? Thanks.
Amazing. Thank you, Scott. Questions? Yeah. Oh.
Yeah.
Is it possible that even if the backdoor is not revealable or visible, that the process of injecting the backdoor is that AI would know that you had access to base?
Well, yeah, I mean, you could imagine an AI that sort of looks for anything suspicious about itself, right? But the idea would be that so like if you look at the Goldwasser et al. Construction, right? Even if you're given the weights, and even if you suspect that a backdoor is there, it is still a cryptographically hard problem to find it. Yeah. Right. If you have the training data that includes the backdoor, then in their case you can that reveals it. So that's why I put this as a research problem, right? You want a backdoor that like is sufficiently innocuous, like maybe the AI sometimes it just normally wants to shut itself down, so it doesn't think anything is amiss if this input leads to it going into a shutdown mode. Alex? Yeah. Yeah. Yeah, so our watermarking method is robust against a user who adds or deletes a small number of words or changes the order of sentences and paragraphs. It is not robust against someone who rewrites it from scratch with the same idea, right? Or yeah. Yes. 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 Good. Yes. Yeah, right. No, I mean, you could imagine an AI that just trains a new AI to, follow its same values, and which will presumably be free of the backdoor, right? The hope is that, like, would you be willing to replace yourself by someone who had been trained on all of your emails, right? I don't know. Like, I feel like I have, a bunch of weird quirks that might be, lost in translation, and maybe the AI would feel the same way. So you could at least, try to bank on that.
Great. I think that's all we have time.
Yeah.
Thanks so much.